Yeah. The simulation takes 2 hours.
Never asked me if I have to. So can I have this?
You gotta rerun the simulation.
This is the equation, the last thing we covered, using it was calculating the inductance of a single phase system or two-wire system. We calculated that one using this equation. Basically, we had only 2 wires. This equation was for m wires. We have m wires. Each one is carrying some current, for example, I1, I2, I3. And the only condition we had, I1 plus I2 plus IN is going to be 0. That was the only condition we had. We calculated the inductance for a single phase system, now calculating the inductance for 3-phase system. So we want to calculate the inductance for a 3-phase system. Let's consider a 3-phase system like this. Phase A and phase B and phase C. This distance is D. This distance is D. And this one is D. And let's call them, this is the A, B, C. And let's assume all of them, they have the same conductor. Basically, the radius for all the conductors are the same. Now we want to calculate the inductance of each phase. How much is the inductance of each phase? Using this equation, I'm going to calculate the flux for phase A. One thing I know here, IA plus IB plus IC is equal to 0, right? This is what we know for a 3-phase system. Balance system. So basically, IA is equal to minus IB minus IC, right? Keep this one in mind. Now we are going to go through the inductance calculation for a 3-phase system. So basically, lambda A is going to be 2 times 10 to the power of minus 7 times. This one is going to go from 1 to 3, right? Basically, it's going to be A, B, and C, right? So let's write it here. So it's going to be IA ln of 1 over, so this K is going to be A. Let's keep in mind. This one is going to be A, right? This one is going to go A, B, and C, right? So first one is going to be IA ln of 1 over DAA, right? DAA is what? We call it R prime, right? Remember, we call it DAA. Let's say the distance of a conductor to itself. Call it this way, because we have a distance between this conductor and the next conductor. For example, we call it DAB. I don't know, this conductor to the other conductor, we call it DAC. But the R prime, we can define it as a distance of the conductor to itself, which is the R prime. R prime we calculated before. So basically, it's going to be 1 over R prime. Plus, now the next one is going to be lambda K is it's going to be, the next one is a B, ln of DAB, right? DAB, K is A, now M is B, right? How much is the DAB? D of A and B is D, right? So basically it's going to be ln, it's going to be IB, ln of 1 over D, plus, now this one is going to be C. Basically it's going to be DAC. Again, in this case, they are equal of, it's going to be how much again? It's going to be DA, right? Plus IC ln of 1 over d. This one.
Is 1 over r prime for IA.
But
1 over r prime for IA prime.
because it's going to be DAA. So you have three. DAA, K is A, right? M is going to be A, B, C. It's going to be DAA, DAB, and DAC. DAA is the distance of the conductor A to itself. How much was it? R prime. We call it R prime. Right? Now, do it this way now. You say lambda A is going to be 2 times 10 to the power of minus 7 times IA ln of 1 over R prime plus, let's factor in this. It's going to be ln of 1 over d ID plus IC. Right? Because I factor in ln of 1 over d. Right? So, how much is this one? This is minus IA, right? Look at here. I can say minus IA is equal to IB plus IC, right? Just by factoring ln of 1 over d, we got IB plus IC. IB plus IC is minus IA, right? Replace it there. It's going to be lambda A is going to be 2 times I'm going to factor in IA is going to be ln of 1 over R prime plus, minus ln 1 over d. Right? So this one is going to be 2 times 10 to the power of minus 10 times IA. Right? It's going to be this one divided by this one, which is going to be ln of d over R. How much is the LA phase A? Lambda A over IA. So basically it's going to be 2 times this is the inductance of phase A for the 3 phases. How much is the phase B? Phase B is the same, right? Because it's going to be the same distance, so it's going to be exactly the same. So LB is equal to LC is equal to LA. So basically 2 times 10 to the power of minus 7 ln of d over. So now we know each phase how much inductance we have for each phase. And we calculate it out. The next one, they call it composite conductor with not equal spacing. We have one conductor. We have one conductor is. We have one conductor is it kind of includes several conductors. They're not equal spacing like here. They're not the same space from each other. Let's say, for example, conductor number 1 is this. Usually we don't have something like this in power system, but this is a kind of extreme case. Let's say we have one conductor here. This is the number 1. This is number 1. This is 2. This is a K. And this is N. See, they are different distances. This is one conductor. Let's say conductor 1 or conductor A. You have one conductor, it has, I don't know, it has N conductor inside, right? So the current in each one is I over N. This one is the I over N, this is the I over N, this is the I over N, and this is the I over N. Right? So we have this current coming, we have an I current going through conductor N, and conductor N has conductor A has an N conductor inside. So the current in each one is I over N. The total current is going to be I, right? Now we have conductor B, for example, it has an M conductor. Let's say this is the 1 prime, this is the 2 prime, for example. This is the 3 prime, and this is the M. And each one is a conductor B. And now each of this one, they have M. This one has a I over M, this is a I over M, this is a I over M, and this is I over M. The only thing, for example, current here is going this way, this one is coming this way, right? When you look at them, they should be opposite of each other. The total of the current should be how much? Should be 0. So we have this system, 2 conductors, each one has kind of, I don't know how many conductors internally. Now we want to calculate the inductance of this system. I'm not going to go through the proof again here. I'm going to jump to the result, and we'll go through one example. We'll go through one example to explain it more, because the proof I don't think so will be kind of interesting for you guys. So conductance, conductor LA is going to be 2 times 10 to the power of minus 7 ln of, I call it GMV over GMR. Here we go, A and R, because this is for LA. And the same thing for LB is going to be 2 times 10 to the power of minus 7 ln of GMB over GMR A. Now what's the definition of GMR? GMR and GMB. GMR A,
The last one is GMRT.
one of them, GMR A is going to be, so basically what, if you go through the proof, what it does, it says, hey, I'm going to come up with a kind of average. I come up kind of average for all these conductors. I model it with one conductor. I have N here. I'm going to come up with the equivalent of one conductor, but I should say how much is R prime for that, right? We know if we had one conductor, it was very simple. We said okay, D over R prime, right? R prime was the radius of the conductor. Here we don't have one to say, okay, is this one or that one or that one. We have N of them. Somehow we should come up with the average of this one. So for this reason, they call the GMR, they call it geometric mean radius. GMR stands for geometric mean radius. Basically, you're finding the average of this radius is here. And we'll put it over here. This is for conductor 1. The GMD, they call it geometric mean distance. Again, when we have 2 conductors, we look at this and this. For this one, we say R prime, right? And we say this distance is D, right? We'll go this way. Now for R prime, it's not as simple as 1, because we have N of them here. Somehow we should come up with a kind of averaging method to replace this one with the equivalent of one conductor. So how much is the R prime for that conductor? That's a GMR. We're going to calculate, we're going to explain how to calculate that. Again here, for example, it's simple. So from this conductor to this conductor is B. Now which one you're going to consider? See, we have 4, it could be this one to this one to this, or that one to this one, that one to this one. We have many of these instances. We need to come up with kind of average again of those instances to see how much it is. So GMR and GMD, they will give us those kind of average. GMR is equal to, for the conductor A, is equal to And I'll explain it now.
Is that n
GMD
squared?
Uh,
Is that to the power of n squared? I mean root?
no, this is pi. Means you know what sigma means, right? We said, for example, sigma I from 1 to 3, for example, ki means k1 plus k2 plus k3, right? You know that.
Yeah.
So it's k1 plus k2 plus k3. When you put pi, for example, I from 1 to 3, ki means k1 times k2 times k3.
I meant in the radical. Is that radical n squared?
Yeah, the root is n squared.
Okay.
This is n squared. But pi I from 1 to n, j from 1 to n, dij. This is the GMR. I'm going to explain it for one example. Let's see what does it mean. And GMD is going to be GMD of A and GMD of B, they are the same. It's going to be square root of mn sigma I from 1 to n sigma j from 1 to n dij.
For GMRA, what's the lowest that's n over 11?
Huh? What?
GMRA.
GMRA is equal to GMR.
Just 5?
This one GMDA is equal to GMDB is this one. Now we said what was the question?
GMRA.
So 11 you said?
Is it n over 11
This one is a pi. Did you listen to me when I was talking to you? You were not here. This is a explain exactly what the pi means, right? Pi means no pi I up to 3 for count ki. This is not 11, guys. This is a pi. This is pi. 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 This is not 11. Sorry, these are pi. So now let's go through one example and see what does it mean. Or before going to the example, let's let's understand, for example, what the GMR is. Look at here, I and J, they are both going to the N. For example, it's going to be D11, D12. See, there's going to be all here. You are dealing with everything here. You know what I'm saying? It's going to be all here. Actually, if I'm going to correct it, this one is going to be from 1 prime to n, right? Because in this side, we call it prime. 1 prime, 2 prime, 3 prime to the n, right? So, GMR, let's look at here, what does it mean here? If it's 2 pi, you know, for example, let's say I is 1, J is going to go from 1 to n, right? So it's going to be pi, let's say I from 1 to n. This one is clear, this is a square root, you know, the root of n squared, you know, of this one. But let's see what does it mean this one. So it's going to be I from 1 to n, this is this part. Let's write the other one. So now I is 1, right? It's going to go D11 for the J1, right? When J is 2, it's going to be D12. Sorry, it's not time. D13 until D1n, right? Actually, this is pi. And we change the J from 1 to n, right? Now let's go for only one term. One term I'm going to go. If I put I1, it's going to be D11. What's D11? R prime, right? D11 means the distance of the conductor with itself. It's going to be R prime, right? Now, look at here. It's going to be for I equal 1. D11, D12, D13, D1n. Basically, look at here. It said we can calculate this, all of them, and time them by each other. One term, right? Time. Now make the I2. It's going to be 2, 1, 2, 2, 2, 3, 2, all the way, right? So, how many of these I'm going to have? I mean, well, how many fluxes? 1, 1, 2, 2, 3, 3, 4, 4.
N.
N. We're going to have n of them, right? So because we're going to use this one like NP, is how much is that one? Is R prime. Basically, it's going to be R prime to the power of n, right? And this one is goes both ways. See, it goes I from 1 to 10 and j from 1 to n. Sorry, it's 10. I from 1 to n and j from 1 to n. Basically, each one is going to be repeated 2 times. For example, we're going to have 1, 1 and 1, 1. You know what I'm saying? 2 times that one. You know what I'm saying?
So is that R prime squared?
Yes, exactly. For each one, it's going to be R prime square. Exactly. How many of them we have? We have n of them should be times 2, whatever it is. So here, now the next term, if you look at it, GMD, if you look at it, GMD is coming from here. It said, okay, if you can put it the same way, it said, go this one to this, this one to this, this one to this, this one to this. Consider one conductor from here and go connected to all of them. Calculate the distance and time by each other. Next one, this, the same thing. Next one, this, the same thing. And you add them all together. This is how we calculate GMD and GMR for this system. And GMRB is going to be ms squared here, and it's going to be pi I from 1 to m, j from 1 to m, dij. Basically like the GMRA, but this time you calculate from this side. You calculate from this side. You are coming with 2. Basically what you are doing here is, okay, so conductor A is equal to this one, conductor B is equal to this one. How much is the R prime for this one? How much is now the neo R prime for this one? Is the GMRA. How much is the neo R prime for this conductor? Is GMRB. Right? And how much is this distance? Is GMD. Basically, you are modeling this system like this. Instead of having 10 conductors for conductor A, I don't know, 24 conductor B, you are coming with one equivalent for each. And you're coming with one equivalent distance for these two. We call it GMD, GMR. Now let's go to one example here to explain this a little bit better.
So these GMRA, GMRB, GMD, we're just modeling each of these blocks as just one conductance across the entire.
Yeah, we're modeling, as I said, the multi-conductor, you know, multi-string conductor with one string. We're coming with that. We know if it's one string, we need an R prime and we need a D, right? But how to replace this one with one equivalent? R prime should be this much, and the D should be this much. We're calculating. Let's go through this example from the book. But usually, let me tell you this. Usually, it's not like this. They are kind of, you know, distributed everywhere. They're bundled, you know, they're all together. They're all the same, very close to each other. And again, the same thing is they're all very close to each other. If this distance is very, very, very smaller than this distance, the GMD is very simple. You know, if you calculate this distance between these two, D, whatever is the D here, you don't have to go through the equation. Because usually it's like this, you know, when you look at the conductors, they're like this, see? And for example, we have another one here, right? And let's say this is the radius R, the radius is R, right? And the distance here is D. If you are going to go with that equation, right? If you are going to go with that equation, we have 7 conductors here, and we have 7 conductors here, right? For the GMR, if I'm going to calculate the total GMR, I'm going to calculate. It's going to be this one, this one, this one, this one, this one, all together. You know, you treat it, you know, and you find the GMR. But now for the GMD, I should go from this conductor to this conductor to this conductor to this. You know, it's going to be a lot. But if this D is much bigger than the R, the GMD is going to be D. You know what I'm saying? If the distance between the two conductors is much bigger than this internal distance between the strings, the GMD is going to be D. You can try once in your life, you know. Try one example, calculate it. It's not going to be exactly D, but maybe it's the 0.999 D. You know what I'm saying? So you don't have to do any more calculation. Say it's D. But the example I'm going to solve now is not like that. They are very different. You know, for example, they are not like centralized like this. They are distributed here, and they have another one here. In transmission line, they are like this. We don't have a conductor like this to be something like this. Let's go through one example here. Solution of both homework number 2 and number 3 will be uploaded tonight, you know. And sorry what is delay for number 2. The email to the class and let you know where the place for exam. If I don't send any email, means we are here. You know, just keep in mind. Yeah. If I send the email, means we are going to go somewhere. I have asked them; they are working on it to see if they can get another classroom for us. So instead here we have a system like this. This is the number 1, number 2, number 3. This is the conductor A. This is the conductor A. And we have a conductor B here. 1 prime and 2 prime. This is the conductor B. The distance here this one is a 0.5 meter. This one is 1.5 meter. This one is 2 meter. And this one is a 0.3. So we have a 2-wire system. This is one wire and this is another wire. This wire has 3 conductors itself. This one has 2 conductors itself. It says calculate the L for LA and LB each one. Separating and the total L, which is going to be LA plus LB in this case. It says calculate those things. And the RX, RA, let's call it RA, is equal to 0.03 meter and RB is 0.04 meter. So each of these conductors, they have a 0.03. 0.03. This one is a 0.04 meter. Now I want to calculate the inductance of this system, LA and LB. Let's start with the LA. If I'm going to, let's calculate the GMD first, right? Let's go with the GMD. So GMD is going to be, what's the N here? N is 3, right? N is how many? 2. So based on what I put over there, the GMD is going to be root 6, right? GMD is going to be M times N, right? So 2 times 3 is going to be 6, right? Root 6 of, now let's write down. It's going to be I from 1 to 3, J from 1 prime to 2 prime, right? So it's going to be pi I from 1 to 3 and pi J from 1 prime to 2 prime, right? Bij. Right? So let's I'm going to write down everything in detail this time, you know, to see how it is. So let's put it this way. It's going to be root 6 of pi I from 1 to 3. I'm going to write this one, right? It's going to be what? It's going to be di 1 prime, right? It's going to be di 1 prime times di 2 prime, right? This is here. For forget this one. I is fixed, is I, right? So j is going to be 1 prime and j is going to be 2 prime, right? Now, let's write this one. So it's going to be root 6. So once I is 1, I'm going to put 1. So it's going to be d1 1 prime times d1 2 prime times d1 3 sorry, I is going to be 1.
Oh, I see. So 2, 1, and
Yes, this is, I'm going to do something. I is going to change now. If I is 1, it's going to be 1 prime and 1 2 prime, right? Now if I is 2, it's going to be 2 1 prime, d 2 2 prime, right? And now if it's a 3, it's going to be d 3 1 prime, d 3 2 prime. One thing you should make sure, it is going to tell you you put all the terms here or not. It's going to be, count how many you have here. 1, 2, 3, 4, 5, 6, and this. If you have 5 terms here, means you are missing something here. So I went with the equation here. But look at it here. It's going to be 1 1 prime, 1 2 prime, 2 1 prime, 2 2 prime, 3 1 prime, and 3 2 prime, right? Basically, to make it easier, you don't have to even look at this equation. It's okay. Hey, this one with everything's over there, right? 1 and 1 prime, 1 and 2 prime. Now the next one, 2 and 1 prime, 2 and 2 prime, right? Now the next one, 3 and 2 1 prime, 3 and 2 prime. So you go one by one from here with all the combination up here, right? Again, the next one with all the combination. The next one with all the combination until everything is done, right? So now let's calculate this one. How much are they? How much is the D1 1 prime from here to here? How much is it?
4 meters.
How much is it? 2, 3, 1, 3.5, 4 meters, right? This is 4. How much is the D1 2 prime? 1 2 prime. Basically 4.3, right? Right? 4.3. How much is the 2 1 prime? 3.5. How much is the D2 2 prime? Here to here. 3.5 and 0.3 is going to be 3.8. 3 and 1 prime is 2. 3 and 2 prime is 2.3. Right? So basically, you time all this thing and you calculate it here to see how much is the GMP. And the number is going to be so it's going to be 3.189. So basically, it's saying this. It's saying, hey, you can replace this system with 2 conductors, which they are how much far from each other? 3189. You can forget that. You can put it this way, right? But now we need to calculate R prime for each this conductor. We need to calculate the R prime for each of these conductors to see how much it is. Now let's calculate the GMR A. Now GMR A. Basically here. So it's going to be root 9, right? Because we have n is 3, right? It's going to be root 9. Now I'm going to write it here first. It's going to be pi from from 1 to 3, pi j from 1 to 3 dij. Let's write it here. So I'm going to write this one first, right? So it's going to be root 9 pi I from 1 to 3 is going to be di1, di2, di3, right? I wrote this one, right? Forget this one. Forget this one, right? It's going to be j from 1 to 3. It's going to be di1, di2, di3 times each other, right? Now let's put this one in. It's going to be root 9. I is 1. D1 1, D1 2, D1 3, right? Now I is 2. D2 1, D2 2, D2 3, and now I is 3. D3 1, D3 2, D3 3, right? Root 9. Usually all these conductors, they are the same R. It could be different, but I'm saying usually it's the same. So basically D1 1, D2 2, D3 3, they are going to be how much? They are going to be R prime, right? Look at here, D1 2 and D2 1. D1 2 and D2 1, they are the same, right? So basically calculate this one just to the power of 2. So basically it's going to be R prime A to the power of 3 times D1 2 to the power of 2 times, again here, D1 3 and D3 1, they are the same, right? So basically it's going to be D1 3 to the power of 2. And the last one is going to be D2 3 to the power of 2. At the end of the day, when you count this one, 2, 2, 2, 6 plus 3, 9 should match this number. Should match this number. Now let's calculate. How much is R prime A? And RA is how much? RA is 0.03. How about D12? How much is D12? 1 and 2. 0.5, right? So it's going to be 0.5. How about 1 and 3? How much is 1 and 3? 2. How about 2 and 3? 1.5. So you calculate this one and you figure out the GMRA is, if you calculate this one, is going to be, so it's going to be 0.3128 meter. And if you do the same thing for GMRA B, D also is going to be 0.09. 0.09667 meter. So now you have the GMD and you have the GMRA and GMRAB. So basically you can calculate each inductance. How much is the LA? And how much is the LB? So you have all these values. You have the GMRA, GMRB, and GMD. If you replace them here, so basically LA is going to be 4.644 times times to the 10 to the power of minus 7 Henry per meter. And if you do the other one, it's going to be 6.992 times 10 to the power of minus 7 Henry per meter. Henry per meter. If you want the total inductance, you should add them together. So basically, if you're going back here, we are equivalent of two conductors. This one has an R prime equal to this much, and R prime B. And this one is equal to R prime B is equal to 0.09667. So this system is equal to this system. This conductor has this much R prime, this conductor has this much R prime, and they're this far from each other. That's the equivalent of that 5-wire system to make it 2-1. But usually the GMR for all the conductors is given. You know, there is a, if you go look at your book in appendix, there is a table A3 and table A4. You know, I'll bring you know, last session I'm going to talk about this one because we're going to finish the capacitor and I'll bring one slide and we'll look at that and we're going to look at that table. Usually GMR is given because usually conductors are like this. They are not like that one over there, but they are like this, you know. For example, I don't know how many we have here, something like this. And you see, if you select this conductor, the GMR is given already. You don't, in reality, you don't need to calculate the GMR for the transmission line. But it is kind of a special project. I don't know even why it is kind of a special. You need to calculate the inductance for that system. You can use this equation to calculate the inductance. Now the next part. How many of you have you looked at the transmission line in the, I don't know, in the desert or somewhere? If you look at them, so there are 3 phases, right? What did you see about this phase? You know, now we're talking about something related to it here. I'm going to talk. You know, what can you tell me about those transmission lines? Before getting there, you know, we have a 3-phase system, right? We want to be balanced. We want LA, LB, LC will be equal, right? We don't want a system, we don't want to have a transmission line. For example, LA is 200, LB is 100, and LC, for example, is 300, right? We don't want that. Why? Why we don't want that? It's going to make unbalance in the system, right? For example, we have a generator here, it's generating a balanced 3-phase voltage. But because we have different values for each line, so at the end it's going to be 3 different things, right? It's not going to be more balanced. So we like to keep it balanced, right? We like to have a LA, LB, LC the same. Now going back to my question. Those ones they have looked at this transmission line. And you see there's either there are 2 circuits, you see they're like this usually, right? They're like power like this. Either there are 3 here, 3 here, or there is just 1, 2, and 3 here. What can you tell me about this? For example, let's look at it. For example, we have a transmission line like this. And one wire is going from here to here. The second one is going from here. And the third one is going here. And usually this distance is very equal. What you can tell me? What is the problem with this? Let's put it this. And let's call this one A, for example, B, and C. Yep.
The effects on each of the wires from the other wires is different depending on which wire you're looking at. So,
yes. But let's say it's easier, you know, based on what we know, you know, we want everybody to understand what this is. Very simple. You know, the 3-phase system, I calculated inductance, remember, it was like this, right? What did I assume they are the same?
oh, D is different.
Right? All 3 they have the same distance from each other, right? Here A and B they are D. B and C they are D. But A and C they are how much? 2D. So if you calculate this one this way, they're not going to end up the same. For example, LA is one number, so basically LA and LC they are going to be equal, but LB is different from the other two. But this is what you have seen it in the outside. So how do we fix this? Let's talk about this and how they fix this. So to fix this one, let's put it this way. So you understood what's the problem, right? The problem is if A is always here, B always here, C here, you are going to end up with a system, it's going to end up with a different inductance for each phase, right? Now we're going to fix this problem. I'm going to put it like this. This is the A, this is the B, and this is the C. A, B, and C. Just I'm showing it from different angle. Let's say this one is here, cross-section of here. I'm doing a cross-section of here. And this one is here, and this one is here. I want to make it completely. So basically this one is, I'm going to call it D1. I'm going to call this one D2. And I'm going to call this one D3. Right? D3. You can figure this from what it is, right? You can imagine what I'm talking about, right? I have 1, 2, and 3 conductors here. And their distances are not equal. The example I give you, A and B and C, they were the same. But here they could be all different, They could be completely different. So basically LA, LB, LC, all they're going to be different. So to fix the problem here, they call it transpose. They transpose it, What does it mean transpose? They said, okay, I'm going to go by average median. How about for the next one? If I bring this one here, in this position, right? Keep it here. This one to this position, right? And take this one to this position. Let's say this is a L over 3. Because I'm going to do this for 3, I will do L over 3. And this is again now. So I did one change, right? The next one again, I'm saying I'm going to do one more time this one. I'm going to bring this one here. I'm going to bring this one here. And this one is going to go up there, right? Now look at it. A was here. A is A here, here, here. Look at the B. Here, here, here. C. Here, here, and here. So all of them is going to be they're going to be in all the position, right? A is going to be on top, middle, and bottom, right? B is going to be on top, middle, and bottom, right? The same thing. So by average, if you look at it as average, So they are like all of them going the same distance now, right? This is another L over 3. And this is another L over 3. And this is the L. Right? They call this one transposing, But transposing is not that easy, Because you think about this transmission line, phase A is coming here, now you have to go change it, bring it here, and take it over there, right? So what they do it maybe every 5. That, you know what I'm saying? 5 of towers are going to A here, A is going to be on the right side all the way for 5 towers. B will be in the middle, C will be on the left side, for example. For the next 5 towers, they put the A in the middle. They do this change as minimum as possible because this one has a cost. To bring phase A from left to the middle, from the middle to the right, you have to pay money for that. But you have to make your system balance. They do it this way. This way by average, so all of them they are going to be in the top, bottom, and middle position equal, right? They call this one transposition.
And need the infrastructure to have 3 of them side by side. Why don't they just have them?
It's very difficult. Think about the tower. This is you see for this transmission line, there are mechanical design. how we are going to do that? Let's think about it. You know, you said why they don't make it equal, you know, to make it easy, and we don't have to do this transposition. Let's say which one is cheaper. You know, we have to do a lot of analysis, but we're going to look at it. His question is this: say we have this tower, right? And I'm going to put the ground here. Now the ground is here, right? Right? Now we're going to do what you said, right? What I should do, I'm going to put this one here. This is one of my conductors, right? I'm going to put this one here. This is another one, right? And now the third one has to come here, right? This is not still good. You know, I can bring this one a little bit this way, and this one a little bit this way. To make these three equal. Right? This is what you're saying. We don't need to transpose it anymore. But what is the problem with this? Can somebody tell me? Hmm?
Essentially, the ground's not the same.
Huh?
Distance from each node of the ground's not the same, so you have an equal.
Is that consistent? You have to keep a minimum distance here, right? Because if you don't do that, what's going to happen? If you walk here, you're going to kill you. You have to have some, like a thunder, right? Thunder, you know, think about how much it is. This is a very high voltage on ground, right? That's the ground, you know? And you know what they have to do, you know, so they have to bring this one up, or they can make this tower very tall, right? But think about the price, because to make this tower tall, you have to deal with the wind. You have to, for example, somewhere you have to deal with the snow. You have to deal with lots of things. You know what I'm saying? So the easier way is to keep them all on the same level, and you will get it. For the system, this is for the high voltage system. They put one here, high voltage, I mean 400 kV and those kind of things. It is like 6300. Maybe you have seen it is like this. Just next time you're driving, check this thing. You know, usually they are like this. They have one here, two here, three here. One here, two here, three here. You know what I'm saying? They have one circuit here, one three-phase circuit here, and one three-phase circuit here. And the distances are good here. They can do this one. Because it's a low voltage. Not low voltage, I'm talking about 60 kV and those kind of things. But not extra high voltage, like either 700 kilowatt, 1 million volt. I'm not talking about those ones, you know. So this distance also, you have to have a minimum distance, right? You have a two-phase. They are, for example, 10 kV or 20 kV. So you have to have a minimum distance. Otherwise, you're going to have a short circuit between the phases, right? When the voltage is lower, this distance is going to be smaller, right? When you have a million kV, you have to have a really big distance, right? So this one has to be as far as from each other, you know, if you can. So you have seen this one. If you see this one, this is because this system usually they have a lower voltage. So this distance is not that big this time. They can put it there. One circuit here, one circuit here. There are two independent circuits from each other. They do this way. Now, so to solve the problem, to keep all the conductors here, and keep the system balanced, what we are doing, we do the transposition. We rotate it, you know, up, middle, down, up, middle, down. This way we can, you know, fix this problem to make the system balanced. Now we're going to calculate how much is the inductance for this system. Another thing about the transmission lines is very, very critical. You know, this design is very critical. When you have a two tower, you got here, you have two towers. So this one comes from here, going here. So this is the minimum, this is the maximum. I don't know what they call it in English, but this is the bend, you know, the maximum bend here. So you should calculate this one for the worst case. Worst case usually happens when?
It's hot.
Summertime, right? Because the cable is going to be bigger, you know, and it's going to be longer. So you have to calculate this one. But think about it. If it is winter time and there is no snow, what is very cold? What is going to happen? This one is going to go up, right? So this one is going to go, for example, become like this. If we design it bad, so let's say this is a very bad engineer. You're a very, very bad engineer. We design it, to be flat. It cannot be flat, but it will be flat. It's going to put lots of tension on the towers, right? Maybe both towers are going to fall down. You know what I'm saying? It happens, sometimes, usually they study for like 20 years, 30 years of, data to see what was the worst case happen. You know what I'm saying? They look at the worst case, and they go design this system based on those kind of things. They call it transmission line design, structure design. The structure is one thing, electrical is another thing. You have to have electrical design, and electrical design will tell you what conductor you should select. A structural design is what kind of a structure you should select, and now all the weight of these wires, I don't know, the weather condition, all those kind of things are coming to do this kind of thing. Now, let's calculate that one. This is, I think, the last, hopefully this is the last topic for the inductance. And,
Professor?
Yep.
So if you say, for the high voltage side, if you do transposing, you have to cross, like, how do you manage with that?
They do it inside, you see, they go from here. For example, internally they bring this one in here, so this one comes here, right? I can bring the phase A here, they put a high insulator on the cable now. You know what I'm saying? They can place, but it's gonna happen every 5 or every 6, you know what I'm saying? That's the reason they don't do it every tower. Because you have to pay cost for this one to bring the wire, for example, from here to the middle. From here to here, you have to pay money for that, right? Because as we mentioned, these are high voltage, right? It cannot, without isolation, we cannot bring it here. It's going to be next to this one, right? The other one is going to go this way, else they're going to pass each other, right? You have to put isolation around it to not cause your short circuit. Without the cost. Now let's calculate the inductance. So basically, what we do, we are going to calculate the inductance for this part, for phase A. This part, and this part, add them together divided by 3, right? That's going to be the average inductance of this system. So, so let's say lambda A1. This is a position, this is 1. This is a 1, this is a 2, and this is a 3. Right? So lambda A1 is going to be 2 times 10 to the power of minus 7. This is exactly what we had for three-phase system. Phase A is going to be our prime A, right? Phase A and B is going to be D1. In this case, say A is here, B is here, right? Distance between A and B is going to be D1. Distance between A and C is going to be D3, right? So let's write it down. So it's going to be, so 2 times 10 to the ln of IA ln of 1 over our prime A plus IB ln of 1 over, so this is a B. It's going to be D1, right? A to B, right? It's going to be D1. Plus IC ln of 1 over, which one? D3. Right? This one for this case was A, B, C, right? A to B is D1, A to C is D3, right? Now let's go for the second one, LA2, lambda A2. It's going to be 2 times 10 to the power of minus 7. And minus 7, again, IA ln 1 over our prime A, right? Yeah, we call it DS. This book is called it DS, or just put in DS, I'll tell you what's the DS. ds is a GMR of A or B or C. They are all the same, right? So if I put R prime on, it means this is single conductor. It doesn't have to be single conductor. It could be many conductor, right? Instead of R prime, just you put ds or GMR, right? You can replace it with GMR. Now, it's going to be IA plus IB ln of, tell me what should be the second position. What's the distance between A and B? See, A is coming here, B is going here, right? Let me put it in the other column. Second position is like this. Now for the second position, this is A, this is B, and this is C, right? They're moving, right? So how much is the DAD? From A to B, the red one. D2. Plus IC ln of what? How much is the A to C? D1. Now let's go for the third one. Times L over 3 also. Lambda A3 is going to 2 times 10 to the power of minus 7 IA ln of 1 over ds plus IB. Now I'm going to put it with the green color. This one is going to be A was here, now A is here. B, the red one is going to go here, B is going to be here, and C is going to be here, right? How much is the A and B now? D2. A and B. You should look at the green color. It's going to be D3, right? Plus IC ln of, how much is it? C and A is going to be D2. Right? So I calculated lambda A for here, and for here. So how much is the lambda A total? So that one is for L over 3, that one is for L over 3, that one is for L over 3. So lambda A is going to be 1/3 of this, 1/3 of that, 1/3 of that, right? So lambda A is going to be 1 over 3 lambda A1 plus lambda A2 plus lambda A3. So why I'm using 1 over 3? Because over the L, over the length of L, is going to be L over 3 here, L over 3 here, L over 3 here, right? So if you do this and do the factoring, see, we're going to have 3 of this one, right? We're going to have 3 of this one. It's going to be 1 over 3 times 2 to the power of minus 7 times 3 IA ln 1 over ds. Now, look at here. I have a ID times 1 over D1, 1 over D2, 1 over D3. I see the same thing, right? So let's factor the ID and IC. It's going to be plus ln of 1 over D1 plus ln 1 over D2 plus ln 1 over D3 times ID plus IC. Right? Let me write it like this.
Why is it 1/3 of lambda A1 standard?
Yeah.
Why is it 1/3?
I said, so here, I want to see how much is lambda from here to here. I'm going to calculate the lambda here, lambda here, lambda here. But for how long is this one? L over 3. For how long there? L over 3. So basically it's 1/3, you know. Now, how much is the ID plus IC? Minus IA, right? ID plus IC is minus IA, right? How much is the ln 1 over D1 plus 1 ln 1 over D2 plus ln 1 over D3? It's going to be ln of 1 over D1, D2, D3, right? So all of them time each other. So this one is going to be ln of 1 over D1, D2, D3. Right? Let me write the rest over. So how much is lambda A? 2 times 10 to the power of minus 7 and 1 over 3. So this one has a IA and this one has a minus IA. Let's do that. So it's going to be times IA times 3 ln of 1 over ds minus, right, ln 1 over d1, d2, d3, right? Let's write this one this way. I'm going to write this one 3 ln of 1 over, right? I can do it this way, right? This 3 can come here, 1 to the power of 3 and this 1 to the power of 3 is the same, right? Factor in a 3 here. You're going to cancel with this one, right? So basically lambda A is going to be 2 times 10 to the power of minus 7 times IA. Here I'm going to have only ln 1 over ds minus ln 1 over root 3 d1, d2, d3. Right? So how much is this one? Lambda A is going to be 2 times 10 to the power of minus 7 times IA ln of d1, d2, d3 over this. And how much is the LA? So basically it's going to be 2 times 10 to the power of minus 7 ln of root 3 d1, d2, d3 over ds Henry per meter. Correct? Henry per meter. Yes. How much is LB? 6. And we did all these things to make them all the same, right? LB and MC, they are going to be the same. There's one more thing I want to say and finish the inductance calculation. The last thing, this is a transposition. The last thing is for very high current, when you have a lot of current, hundreds, thousands amps, something like that, you know. So what is the problem when the current goes up? What we have to do? If you have a 10 amps, say what is gauge 14 or gauge 25, right? If you have a, I don't know, 15 amps, say I have to have a gauge 10, for example, right? What you are doing, you are making it bigger and bigger, right? When the current goes up, you are making the conductor cross section bigger and bigger, right? If you don't do that, what's going to happen? It's going to burn. Why? Because there is a RI square loss, right? R is depending to the conductor and I is the current we are going to pass. So if you keep the current, the conductor small, the cross section is small, R is going to be bigger, right? R is L over rho L over S, right? If S is small, R is going to be bigger, right? To fix the problem, to reduce the ohmic loss, to prevent the wire to burn, we say, hey, use the bigger wire. If you use the bigger wire, so basically the resistance is less, and the power loss is going to be less, and it's going to be less heat generated inside the conductor, and it's going to protect the wire, right? Now, when we have a big, transmission line, it's going to transfer a gigawatt something, now we are going to deal with a huge current. So one way to solve the problem is the way I said. They call it two-circuit systems. This tower, they have one circuit on one side and one circuit on the other side. We make it like a half and half, right? But usually for high voltage, we cannot use that one because because of the distance, it's going to be a problem. What they will do, they do this one. They bundle. This one again represents one conductor. This conductor could be many conductors inside this. So for me, they use it this way. They say bundle. They use two of them next to each other. For example, again, this is a transmission line. This is a phase A. I am sure you have seen this one. Those ones, they have looked at this transmission line. They have something like, this is just phase A. Keep in mind, this is just phase A. Phase B, the same thing. They bundle it. They use two for one, this phase, two for that phase, and two for the other phase, right? Can you tell me why they tie them here together? Why? This is phase A, right? This is phase A. This is A and this is A, right? Doesn't matter. If they touch each other, there is no problem. They are the same, right? Why do they bundle? Because why do they? This is already bundled. When we have two, it's already bundled. But why do you put this kind of holder here to keep them together? They don't want to go like this and hit each other, because every time they hit each other, even they have the same voltage, it still is going to cause transient in the system. It's not going to blow anything, but it's going to cause lots of transient. They want to keep them the same. They want to keep them like one conductor. There are three different combinations. It could be two, it could be three. This distance is D. Or they can put it this way. Next time you are going to, for example, Phoenix, look at this one, they have the one over there. When you go from Highway 8, they have this one over there. And it could be this square. Again, D, they call it bundle. They bundle them together. So when we bundle them, what parameter is going to change in the inductance? We said in general, inductance is 2 times 10 to the power of minus 7 ln of GMD over GMR. Does this one change the GMD? No. Why? Let's do the real case. So when we have a real case, I'll finish this one quickly. So when we have a real case, for example, we have one here, I'm going to put just two. One here and one here. For example, this one is about like 10 to 20 centimeters, something like that. This is a high voltage system. But this one is maybe 10 meters. You know what I'm saying? And I said, when I talked about this composite conductors, I said if the D is much bigger than the distance between these conductors, means nothing. The GMD for these two is going to stay this, right? And this two is going to be equal to 1. So the only thing that's going to change is going to be GMR. So how much is the GMR? Now this is like a two-wire conductor, right? How much is the DS for this case? Somebody tell me. How much is the DS? N is 2 here, right? We said what? We said N is 2. It's going to be root 4, right? Pi from 1 to 2. Pi from 1 to 2 Dij, right? So it's going to be D11, D12, D21, and D22, right? So, and D11 and D22, they are the same. What they are? They are R prime, or DS, right? So let's call this one DSL, D bundle. This is for the bundle. So basically it's going to be root 4, DS, DS, and, I don't know, let's call this one D and D, right? It's going to be this one to this one, this one to this one. How much is it? It's D and D, right? This one to itself, how much is it? DS, or GMR, or R prime, right? We said you use a DS to show that. How much is this one? DS again, right? So basically it's going to be DSL is going to be D, DS. DS is the GMR of this one. GMR of each conductor We call it ds or r prime. If it's a single conductor, ds is r prime, right? So how about this one? DSL, I'm going to write the answer right away. I'm going to have 3 of this one, right? It's going to be root 9. Basically, I'm going to have a ds to the power of 3, right? Because I have 1, 2, 3. How many d do I have? 6, right? It's going to be d to the power of 6. 6 and 3, 9 and 9, right? So basically, it's going to be root 3 ds d2, right? And the last one, DSL, is going to be root what? 16. I have 4, right? Root 16. How many ds I have? 4. ds 4. How many d I have? 1, 2, 3, 4 times 2. 8, right? So actually I'm wrong. It's going to be d 12. 1, 2, 2. No, hold on. I made a mistake. There's a 1, 2, 3, 4. So it's going to be d to the power of 8, right? And what else? Look at here. This one and this one, right? I missed this one. How much is this one? This is a square root of 2d, right? I have 2 here and 2 here, right? So it's going to be the square root of 2d to the power of 4. See, I have 1, 2. From here to here and here to here, right? From 1 here to here and here to here. So this one is going to be how much? I don't know. It's going to be... It's going to be 1.09 So this one, the DSL is going to be 1.091 root 4 d d3. We're done. So if we make it bundle, we use this. But all of this one is going to go back to the GMD GMR. If you know how to calculate GMD GMR, all these things are based on the GMD and GMR for the conduct. Tuesday we have a midterm and a certificate.